Hello and welcome to Empowered Learning Video. So this is the third video in the Laplace transform video series. And in this video, what we are going to do is go over some special properties of the Laplace transform. Mainly, we want to go over the linearity properties as well as our translation properties or transformation properties. Basically, how do we deal with horizontal shifts in the t or time domain, as well as how do we deal with the horizontal shifts in the S or Laplace transform domain. Okay, so after we do that, we're going to do several examples of just taking the Laplace transform of general functions. And so we'll be using our charts to be able to come up with those Laplace transforms, because it'll be either sums or differences of several functions with some shifts in it. And so we're going to use what we talked about in the first two videos, as well as what we're going to talk about in the beginning of this video, to be able to help us to be able to get those Laplace transform equivalent functions. So now that we've actually established some Laplace transform identities in the part 2 video, we're actually going to use that along with some of these helpful hints and properties to be able to basically use as a tool for whenever we actually have to take the Laplace transform of an ordinary differential equation. So we're still trying to build up to that. So let's first go over our linearity properties. These are properties that whenever we learn a new operator, we usually want to check these things out. And so, of course, a lot of these will make common sense to you. If we have, let's say, a Laplace transform of two functions here, and we say that we have two real number constants, alpha and beta, then what we're saying is if I take the sum of a constant multiple of both of these functions, f of t and g of t, then I can show that what that ends up being is really just the Laplace transform of the original function times that constant multiple plus the Laplace transform of the other function times that constant multiple. And of course, this makes a whole lot of sense, because remember that the Laplace transform itself is just an integral, okay? And I'll just write it with this first one here. And of course, one of the things that we know is that with integrals, any constants that we have, we can just factor out, okay, the integral. So this would literally be like alpha times this improper integral. And of course, we could slide that alpha back in there to make it look like this. So that's why we don't really spend a whole lot of time talking about this particular property. But of course, we have to verify that it's true. We know it is, so we just move on. This second one here is just an extension of what we're saying for this first one. So we're saying if we have n number of functions that have constant multiples being multiplied by it that we want to take the Laplace transform of, then of course, just like how we did the Laplace transform of these two, we would do the same to all n of these functions. Okay, so not much to write home to your mom about there. Okay, so if we look at example 8, we'll see an example of how this works. So we have a Laplace transform of constant multiple of t raised to the 4, and we have a Laplace transform of constant of the function sine of 5t times constant of -6. Okay, so we could really view this as this plus -6 times sine of 5t. Of course, that would be like that. So constant multiple times function plus constant multiple times another function. And we want to know what's the Laplace transform. Well, we know from one above here, we know from this, we can just rewrite what we have here as constant multiple times Laplace transform of the first function plus -6, which is just -6 times Laplace transform of the second. And so from here, we look and we see what is the Laplace transform of t raised to the 4. And of course, we've already found out that the Laplace transform of t raised to the 4 was 4 factorial divided by s to the 5, s to the 5th power. And so what I'll do here is we'll see where that is in our actual Laplace transform table. So we switch here and go to a Laplace transform table I've written here. So you'll see if we keep scrolling down, eventually we'll get to Laplace transform that we want here. And the one that we want is this one, okay? So when n is equal to 4, here we put a 4 here, put a 4 there, and we see that we end up getting that 4 factorial divided by s raised to the 4 plus 1, or just s raised to the 5. So that's where that's coming from, okay? So we'll go ahead and switch back now. So we see where the Laplace transform of this comes from. If we look here for sine of 5t, we know that the Laplace transform of that, I'll just go ahead and write it here. Laplace transform of sine of omega t is just omega over s squared plus omega squared. And again, if we look in the Laplace transform table, scroll down, we see that that is right here, okay? So once we actually put in all the information, then it's just algebra bringing it together. And we see that the result just ends up being 72 over s raised to the 5 minus 30 over s squared plus 25, okay? And it's actually a little advantageous for us to leave it this way. And I'm saying that because in how we're going to use this in solving ordinary differential equations, you're going to see that if we could actually write our Laplace transform of our solution to the ordinary differential equation in this form, it makes it very easy for us to look and see how that pairs up with a matching Laplace transform, or we may have to do some algebraic manipulation to get it to match up. But once we can do that, we can just translate directly what we are going to call the inverse Laplace transform in my next video to figure out what the actual solutions to the ordinary differential equations are. So you're going to see that if I can actually rewrite this in this form, or leave it in this form here, I'm going to do that, okay? All right, let's move on to the next example. All right, so for this next example, I'm actually going to work it out so that we can kind of feel the flow of this if we're actually doing it in real time. So if I want to find a Laplace transform of this function here, of course, I want the Laplace transform of all of this. I'm just going to write it all together. And remember, this u sub 6 here is a unit step function that has been shifted horizontally to the right by 6 units. Okay. And of course here we can take each term, the constant multiple, we can just leave that on the outside. Of course, we got our hyperbolic function here. And that's 10 Laplace transform of u6, and that should be u6 of t. So let me fix that. And then minus 12 Laplace transform of 1. So first thing we want to note is the Laplace transform of each of these functions here. I'm just going to list them out one by one. keep on doing that for the unit step. All right, so use 6 of t. And then, of course, Laplace transform of 1. All right, so if we go to a Laplace transform table here, what you'll see is the Laplace transform of 1 is just 1 over s. So we see here that that is just 1 over s. If we look for the Laplace transform of unit step, so we see that the Laplace transform is just e raised to the minus alpha s divided by s. And remember, we found that. So we'll come back here. So this will be e raised to the minus 6s over s. Now we look for a sine hyperbolic of pi times t. So we'll see if we have that in our list. Yep, and we do. Sine hyperbolic. A is going to be the same thing as pi in this case. So we're going to have basically this will be pi here, and that will be pi there. So we'll have pi over s squared minus pi squared. So we'll just do it like that, and I'll go ahead and erase this because I'll probably need to use this again. So we'll have pi over s squared minus pi squared. And then, of course, Laplace transform of t squared. If we go back, we'll remember here that that was this one here. And just so that you know, there is a difference in between this one and this one, where this alpha could be any real number, whereas n can only be natural numbers. So n can only be 1, 2, 3, 4, where alpha, again, could be any real number as long as it's greater than -1. Okay. So we see here that Laplace transform of t squared is just going to be 2 factorial over s plus 2 plus 1, which is s cubed. So we'll just say 2 factorial over s cubed. So here, in noting all that, all we have to do now is just go ahead and write all that stuff in. So I'll just come bring this down here and just say this is 5 times 2 over s cubed, because we know 2 factorial, that is just 2, minus 7 times pi over s squared minus pi squared. So erase that. And then plus 10. We know that here the Laplace transform of the unit step shifted 6 units to the right. It's going to be e raised to the minus 6s over s. And have minus 12 times 1 over s. And of course, all we have to do now is just bring it all together. So this is just 10 s cubed minus 7 pi over s squared minus pi squared plus 10 e to the minus 6s over s minus 12 over s. And of course, if we want, we could combine both of these terms here and just say that this is minus 12s like that. And get rid of this if you like. And we'll just keep it that way. And so this would actually end up being the Laplace transform of our total function f of t. And we could also call this big F of s here. And so this is basically how we deal with taking the Laplace transform of some general function here. Okay, so we've seen an example of how we deal with taking the Laplace transform of a function where it's really comprised of the sum or difference of constant multiples of functions that we already know. Now we need to talk about what happens whenever we have transformations or translations, as some people call them, in our f of t function or in our Laplace transform equivalent. So we're going to see what that looks like on both sides of the house, so to speak. So again, we're going to consider that we have the Laplace transform of two functions. We're going to have all these real numbers, s, alpha, beta, and gamma. And we're going to make the condition that whatever s is, it has to be greater than whatever alpha is. Okay? Everything else could kind of be whatever it wants. So one of the important properties that we note here is that anytime we have the Laplace transform of some function times e raised to the alpha t. So let's say if we take any function and multiply it times an exponential e raised to the alpha t, where again, remember that alpha is going to be a number smaller than s, then what this turns out being is an actual horizontal shift in the s domain or the Laplace transform domain, okay? And so how we're going to use this is, let's say if I wanted to take the Laplace transform of some function, but it shifted alpha units to the right. Well, what I could do is just say that the Laplace transform of whatever this is, I can just look at this, take the Laplace transform of it, find out, inverse Laplace transform of it, find out whatever f of t is, and then say, let's multiply that times e raised to the alpha t. And so that's what I would do if I was doing an inverse Laplace transform, which I'm going to be talking about that in my next video. Now, moving forward, which is how this is originally presented, if I have e raised to the alpha t times some function, then all I have to do is concentrate on taking the Laplace transform of this function and then shifting it by that amount, okay? So I talked about it in two ways because in all actuality, this is an identity, so it can actually work going from left to right. It can also work going from right to left, okay? Now, from a conceptual standpoint, what is happening is that anytime we take a function and we want to take the Laplace transform of it, but that function comprises of another function times an exponential, the exponential part of this entire function here is actually causing a shift in the s domain for this particular function. And if we think of the s values as frequencies, then what we're saying is we're shifting, when we do the Laplace transform of this function to get it like this, it's really just this function, but we have a shift in frequency by alpha units, okay? Depending upon what we're measuring frequency in radians per second or hertz, that part really doesn't matter. Just know that there's going to be a shift in the s domain, okay? Now, of course, if alpha is itself a negative number, then of course this would be s minus a minus number, and of course this would end up being plus at that point, and that would be a horizontal shift to the left, okay? But again, main thing, Any function multiplied by e raised to the alpha t in the time domain means that we're going to have a horizontal shift in the frequency domain. And I'm calling the frequency domain the domain where the Laplace transform is, and the time domain where we just have the values t here for f of t. All right, so our next transformation kind of lets us know, well, what happens if we kind of flip the situation here. So let's say we want to take the Laplace transform of a function, and that function has a horizontal shift in it. Well, what does that look like in the S domain or the frequency domain or the Laplace transform domain? Okay, I'm trying to use it in all three ways. So what this is going to look like here is that we're just going to have a Laplace transform of the actual base function, but we're going to multiply it times a factor of e raised to the negative s alpha. Okay. Now, remember that s is a constant and alpha is a constant. So e raised to the minus s alpha is itself just a constant. Okay. So effectively, what we're doing here is we're saying that if I have a horizontal shift in the time domain, then what that's going to do in my frequency or Laplace transform domain is either increase the amplitude of my function or it's going to decrease the amplitude of my function. Putting that in algebra terms, that means that either I'm going to have a vertical stretch or I'm going to have a vertical compression. Okay. Now, of course, if S alpha is greater than 0, okay, so if this quantity here is greater than 0, so let's say it's like 1, then of course this is a value that's greater than 1, and that means that my actual function big F of S is being vertically stretched. Okay, so this happens here whenever that quantity is greater than 0. Now, of course, if this quantity here is less than 0, like saying e raised to the negative 1, then of course that's going to be less than 1, and to be specific is going to be in between 0 and 1. So of course we're going to have a horizontal compression, which means the amplitude, if you will, of our particular big F of S is going to be decreased or compressed. Okay? And so again, main thing here, horizontal shift in time domain means that we're either doing a vertical stretch or a compression in the frequency or Laplace transform domain. And depending upon what the quantity of this particular number is, if it's positive, then of course it's a vertical stretch. If it's negative, then it's going to be a vertical compression. For our last translation property, we see here that if we are taking the Laplace transform of some function, and that function is either being horizontally stretched or horizontally compressed, okay, because that's what it means to have a constant being multiplied times t here. So let's say if we had, just say sine of x, then of course I know sine of 2x means that I've taken my sine function and I have horizontally compressed it. Okay, if you want to think about that in other terms or practical terms, I have increased the frequency of sine of x by 2, or put another way, I have increased the period by a factor of 2. Okay. Similarly, if I had sine of 1/2 x, I have stretched out or increased the period of that function by a factor of 2. Okay, I've made the function longer or horizontally stretched it out. So we see here that we have a horizontal compression whenever my alpha is greater than 1, and we're going to have a horizontal stretch whenever my value is in between 0 and 1. Okay. Now, what does that translate to over here? So, and I'll just use actual values here. So let's say alpha is 2, okay? So if alpha is 2, then I'll put a 2 here and a 2 there. So what we essentially have in this case is we have f of 1/2 s. So we know that the 1/2 here is letting us know that we have a horizontal compression, a horizontal stretch. And here we know that because we have the 1/2 here, this is the vertical compression, okay? So what I'm trying to get at is that if we have a horizontal compression in the t domain, what that translates to in the s domain is going to be our Laplace transform function being horizontally stretched as well as being vertically compressed. So to put that in layman's terms, if I'm making my function skinnier here, I'm going to make my function wider and shorter here, okay? So skinny function here means wider and shorter function here, okay? Now, the exact opposite happens whenever we let our value of alpha be in between 0 and 1. So let's say instead of 2, we use 1/2, okay? So if we use 1/2, the exact opposite happens. If I use 1/2 here, then I'm making my function here fatter or wider, okay? So I'm making my function wider here because I'm doing a horizontal stretch. Well, I know here if I put a 1/2 here and a 1/2 here, that's going to be the same as 2 times big F of 2s. The 2 on the inside here makes whatever function that I have get skinnier, and this 2 here, since it's greater than 1, makes my function get taller, okay? So essentially, if I'm wider here, if I do something to make my function in the time domain or t domain wider, that's going to translate to a function in the Laplace transform or s domain being skinnier and tall, okay? And so that's one way we can kind of think about what's happening when we do that actual transformation of f of t to big F of s. All right, so now we are going to close out. We're doing some examples of taking Laplace transforms where we're going to see some of those transformation identities that can be used. So we see that in our first example here, we have f of t is equal to e raised to the negative 2t times sine of 4 divided by pi times t. And so right off the bat, we notice here that we have the Laplace transform of something that looks like this, okay? And if you remember, we said that anytime we took the Laplace transform of a function being multiplied times e raised to the negative alpha, or alpha t, I should say, then we know that that was just going to be a horizontal shift in the s domain. And so let me take that off here. So if we look here, just going to go to my little chart here, we see that here we see that that's exactly what's happening here. And of course, we know that s has to be greater than alpha. So as we make that assumption, and that of course ensures that whatever this value is in here is going to be something that's greater than 0. So with that, all we really need to do is figure out, well, what is going to be the Laplace transform of this? Okay. So this is going to be our f of t. So that means here, what is going to be the Laplace transform of sine of 4 divided by pi times t? Again, we'll look here. And we see that for sine, it's just omega divided by sine squared plus omega squared. So we just come here. We know that omega is just going to be 4 divided by pi. So we'll just say 4 divided by pi here over s squared plus 4 divided by pi here squared. And so, of course, this ends up just being 4, and I'll just do, what's it, pi s squared here. And this will just end up being 16 over pi squared. So when I multiply that times the pi, this will end up being just 16 over pi. And of course, if we want to get rid of the this fraction in the denominator altogether, we could just multiply this by pi here, pi there, and we just end up with 4 pi over pi s. Well, let me not do it like that because it'll kind of mess up what I'm going to do next. So s squared plus 16. Okay, so that is what the general Laplace transform would be. So we know that f of s minus alpha, and of course, alpha in this case is going to be a -2. So that's just going to be f of s plus 2. And all that does is take my s that I have here, and we just replace it with s plus 2. And we see that will end up being what the Laplace transform of this particular function would be. So for our last example, we see that we want to take the Laplace transform of t plus 4 quantity cubed plus 6. And we can easily recognize here that the base function for this, well, I really shouldn't say base function, but we know that the base function is t cubed. We know that we have a vertical shift upward of 6 units, and we have a horizontal shift to the left of 4. We're not really concerned about this vertical shift up, but we are concerned about this horizontal shift to the left 4 units here. And so we'll look at the function this way and note that we have some horizontal shift. So if we wanted to do the Laplace transform of this particular function here, then what we would do is just really split it up into 2 separate Laplace transforms. So we'll have this plus Laplace transform 1, and of course multiply that times 6 there. Now we see that for a Laplace transform of t plus 4 cubed, that's going to be a horizontal shift in the t or time domain. Okay, so if we look at what our shifts tell us here, or what our identities tell us here, we see that whenever we have a shift in the t domain, that means that we're going to be multiplying our base Laplace transform function by a constant of e raised to the negative alpha times s, or s times alpha. Okay, so if we note what we just said here, then that means that of course this will be e raised to the negative s times alpha. And of course, our alpha in this case, since this is a plus 4 here, this will be like minus a -4. So this will be minus a -4 times the Laplace transform of t cubed. Okay. And this will end up just being e raised to the 4s times Laplace transform of t cubed plus 6 times Laplace transform of 1. So if we go and look back at our table here, we'll see that the Laplace transform of t raised to a positive integer is just going to be that integer factorial divided by s raised to the n plus 1. So in this case, we know that this will just be 2 factorial divided by s raised to the, sorry, that should be 3. I don't know why I wrote 2. So this should be 3 factorial divided by s raised to the 3 plus 1 here. And the Laplace transform of 1 is just going to be 1 over s. And of course, if we look at our table again, we will see that right here. Okay. So now we just bring it all together. So 3 factorial is just 3 times 2 times 1, which is 6. So we'll have 6e raised to the 4s and plus 6 over s. And of course, all that's going to be divided by, for the first term, s raised to the 4. So yeah, forgot to write that. And so this ends up being our final answer for that. And so you see now that we've kind of started from the beginning, we've built our knowledge about the Laplace transform. We understand what type of functions we can use with it. What are those conditions that need to be satisfied for those functions so that we can actually take the Laplace transform of it. We talked about some important identities. We see how we've actually used our Laplace transform charts to be able to take the Laplace transform of functions. And now we're actually ready to move forward and try to actually solve ordinary differential equations by using Laplace transforms. And so the next video is going to go over that, and that's when we're actually going to talk about the inverse Laplace transform and how we use that practically.